Greetings.
And salutations.
Chapter 2, Section 6 coming at you. More rational function stuff.
Well, I don't know about more. We've
looked
done
at,
some. Okay, a rational function.
Maybe not a rational function, but we've looked at rational numbers.
We've looked at rational stuff. Yeah, definitely. So what happens to make it a rational function is that we have, basically, we can split it up into two polynomial functions, a function on top and a function on bottom. So basically, we just have to have a fraction, and then bam, we've got a rational function.
Which we have seen with our synthetic division and stuff like that. We just haven't addressed it specifically like we're going to today.
Until now.
Right.
Okay, so here's an example. Find the domain of a rational function, f of x equals 1 over x minus 2.
Real quick, while we're talking about the domain of this, one thing to remember is that you just can't have 0 in the denominator. Wait, that is domain.
Oh, yes. That's how you figure out the
You cannot
domain.
have a 0 in the denominator of any rational function. It's just not a good deal.
So when we're doing rational functions, you want to take the bottom,
whatever it is,
and you want to set it equal to 0. And what we're saying is that it can't equal
that is
whatever
correct.
that number
Can't
is.
have a yeah.
So I'd add 2 to both sides here. And I'd very quickly come to the conclusion that x cannot equal 2. But any other number is fine.
Right.
What we're saying with this is if I plug in a 2, I get 0 on the bottom. 0 on the bottom is undefined. You can remember because it makes an upside down stick figure. That upside down stick figure is sad because he's undefined.
What if that was like a 3 up there? Could he still be an upside down stick figure?
That would be a much more awkward stick figure.
Okay.
But I think you maybe could make it work.
All right, I'll work with you on that.
Okay, so to write this in interval notation now, we go from negative infinity to 2.
But we can't include the 2 because that's where the 0 happens.
And then 2 to infinity. And remember, if you put a bracket, don't change it to a parentheses like so.
No guessing game on this. Okay. We want to know.
Erase. Erase if you make a mistake. Because it's very important that that's parentheses because it's not equal to it too.
That is correct.
And if you look at the graph on this, like I know exactly what this looks like. We would have basically a vertical asymptote.
Yeah, at 2.
At 2.
Because our graph of 1 over x actually shifts 2 units to the right.
And there's also one at y equals 0. And so what happens is your graph will do like this thing, I think, if you're looking at it. And look, clearly there's nothing defined at 2.
Nothing at all.
But algebraically, it's pretty easy.
Yeah, not bad.
And in case you're like, oh no, what about square roots? Square roots aren't polynomials, so we don't have to deal with that in this section. We just have to worry about where does the bottom equal 0. And
one of the problems that you're going to run into is a lot of times the pre-calculus kids want to make the top equal 0 also.
Which tells us something, but nothing about the domain.
Yeah, you can have the top equal 0. That's totally legit.
That gives you X-Intercepts, actually, which is something we're going to do in a little bit.
So bottom only.
Bottom only for domain. Command Shift.
Okay, so keeping along the lines of where we are and are not defined in the denominator, we can actually describe how a graph can be obtained from the reciprocal function.
Yes, all of these, if we think back to in Chapter 1, we talked about parent functions. And so most, if not all, I don't know, would you say all of them are related somehow? Maybe just most. I think most is good. A lot of the functions are going to be related to this g of x equals 1 over x, which remember that what that looks like as far as our parent graph goes is that we've got a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. Then we've got this cool looking thing right here in the first and third quadrants. And so what the rest of these will look like is they'll have some kind of a stretch, shrink, shift thing going on.
So it should have the general shape.
Yes, the general shape should still be consistent. So in this problem, they want us to describe how the graph of the given function can be obtained by transforming the graph of the reciprocal function. And also identify the horizontal and vertical asymptotes and use limits to describe the corresponding behavior. Lastly, sketch the graph of the function.
Wow, that's a bunch.
It's a lot of stuff.
So one thing to remember is that after we did all that practicing on sliding graphs all over the place, remember if you do something to the x, like actually to the x, it's going to become part of the super secret opposite society, which is a big deal because on this first one, without doing a lot of work at all, we're looking at that guy, and with the x plus 3 in the denominator, we're adding 3 to the x, which means that super secret opposite society, we're going to move 3 units to the right.
You mean left?
That's what I said.
Yes,
left.
We're shifting.
The opposite of plus 3.
Shift left 3. Because that plus 3 is inside of our function. Our function is 1 over x, and the plus 3 is inside of where that x is. So shift left
3 units.
3. What else is happening to this?
We also have a vertical stretch of 2 going on. Now, why do I know it's happening not to the, specifically to the x? Because notice that your x is in the denominator, and we're not dealing with a number in the denominator right now. We're dealing with a guy in the numerator, and so that would become outside, and we're going to do a vertical stretch by a factor of 2.
I'm thinking we're probably going to need some room here, so I'm just gonna we'll
do an A and B
clean
version.
it. Yeah,
Right.
Vertical stretch by 2, and those are the 2 things we've got going on. We could also end up seeing like reflections. We're not going to see typically horizontal stretch or shrink. They're not going to necessarily stick a 2 down here on the bottom. We're going to see them on the outside,
Usually,
because of the nature of the way they're setting the problems up.
Right.
So that's the transformation. Identify the horizontal and vertical asymptotes. So the vertical asymptote, that's easy. That's where the bottom equals 0.
So
always. That's how we find
x
it.
plus 3 equals 0. The other, if you want to work it out, do it. I usually will ask myself in my brain mentally, quietly to myself, what plus 3 equals 0?
And you get -3.
And you get -3, and that's your vertical asymptote.
So is there a slide somewhere in here that talks about how to find the horizontal asymptotes?
I believe we have addressed horizontal asymptotes, but in this
case... We
case...
talked about graphing them. Like if I graph this, like originally my parent function has y equals 0 as a horizontal asymptote,
Right.
and we didn't move up or down, so this still has to have y equals 0 as a horizontal asymptote.
One way that you could also remember that is if you think about really large numbers of x, like 2 jillion, trillion, billion, million, jillion.
Yes.
Then if you put that number into the denominator,
And you do 2 divided by
all of that plus 3, then you get a number that's really, really close to but not quite equal 0, and that will give us our horizontal asymptote as well.
Okay. And we'll talk more about horizontal asymptotes apparently later on.
A lot more.
Yeah.
There's some cool tricks.
Yeah, and then use limits to describe the corresponding behavior. So what we want to do when we use limits is we want to use a limit for our -3 that we've got, and we want to look at 2 different limits. We want to look at the limit as x approaches -3 from the negative direction.
That means from the negative side of the number line. Let's just keep it easy.
This is g of x, not f of x. So of our function.
And so as you zoom in from the negative side of the number line,
what is it getting closer to? So basically it looks like this, but we're going to pretend this is at -3 instead of it being the y-axis.
so notice on the graph at that point, I'm looking right at it's going down.
As we're getting closer to -3 from the negative
from
direction.
the negative direction.
So that's this
down,
direction.
down,
Where are we
down.
going? We're going towards the negative infinity. And so you'll see this notation in the book and here in our notes as we do it. So now we're going to approach -3 from the positive direction.
So that's coming from the other side now, which means that from the positive side of the number line, we're going to approach an x value of -3. And when you do that,
You're getting closer and closer to positive infinity this time. And those should be opposite because we were heading opposite ways whenever we came up to the asymptote for either direction.
Right.
The other type of limit we should look at is for our horizontal asymptote. That's our in behavior. So our in behavior is as x approaches -infinity, what value am I getting closer and closer to?
And that would be the actual asymptote number, which is 0. Remember, with a limit, you're looking at what happens when you get really close to a specific x value. What y value does your graph approach? And so in this case, it never actually touches 0, but it gets really, really close to 0. So that's what the limit is.
I feel like you just called me a 0.
I would never call you a 0, Mrs. Stevenson.
Okay, just so we're clear.
Right.
And then sketch the graph of the function. So we've kind of got a sketch that we've been working on up here, but let's go for it one more time.
Let's do
If
it.
I was sketching this, what I would do is I would say, okay, I know there's a vertical asymptote at -3. So I would draw a dotted line at -3. There's a horizontal asymptote at y equals 0. So here's our horizontal asymptote.
And remember, this is a sketch, not a perfection.
Right. And then if you need to here, we can plug in some numbers. Like we could plug in 0, which is over here, x equals 0, and we could say, oh, that's 2/3. So at 0, I would be at 2/3, which is about right here. And then that will help you realize, okay, my graph really is up in the top right, and then We can also plug in like a -4 if we wanted to. We'd get 2 over -1, which is -2. So that tells us it is down here. And that will help you figure out which part of your graph, because sometimes you end up with it in the top left and bottom right instead of the...
Right, sometimes it's kind of an upside down mirror
thing.
Yeah.
Yeah. And that's all for A.
Okay, so we're going to look at B. Hey there!
Now we're trying part B. So this one's just a little bit tougher because this has an X on the top and the bottom, and that's not what our parent function looks like.
No, it doesn't look like that at all. We want the same general shape.
Right, so what we can do is we can use division and make it look like it. And so on these, the book generally makes you do like long division, but there's no reason why we couldn't do synthetic division.
The book, synthetic division, way easier.
So remember, if I'm dividing by x minus 2, that I change it to a +2. Okay.
Wow, this looks really hard. There's a lot of stuff going on.
So move the 3 down. Times.
And you probably shouldn't get a 0 in this case.
No, you shouldn't. Otherwise, you did something wrong.
Yeah.
So what we're saying, if we write this back as a polynomial, is that h of x equals 3, because remember, it's 1 degree less than what we started off with.
Start off with first degree.
So now it's 0 degrees. So 3 minus 1 over x minus 2.
Wow, that's really easy.
And now what we can do is we can say, well, this the +3 on the outside is telling us that we've got a shift up of 3.
Mm-hmm.
The -2 on the bottom is telling us that we are shifting right 2.
Righty. Super secret opposite society down there.
And then lastly, the negative right in front, that's a reflection across the x.
Yep.
Excuse me, reflection across the x-axis.
Reflect over x.
Because remember, they would have to actually have made the x negative. Like our negative would have to be down here on the bottom
and
for
it
to be a reflection across the y-axis.
Right.
So it's reflect over x-axis. That's our first thing. And so really, we could go ahead and draw this right now almost if we wanted to. I misspelled right. Let me fix that.
That's okay. Fix your misspelling.
Okay.
That's why we teach math, not English.
Yeah, exactly. So identify the horizontal and vertical asymptotes. Well, if we graph this,
it's easier to see the horizontal and vertical asymptotes.
Absolutely. We know from the previous slide what a normal reciprocal function looks like. We're shifting up 3, so we have a horizontal asymptote at 3. We're shifting right 2, so our vertical asymptote should be at 2, because normally they're both at 0.
Right.
And then we're reflecting over the x-axis. So instead of having our graph be at the top right and the bottom left, that means we'll be bottom right and top left. Got a little close to the asymptote there.
That's all right. And you can always check this by picking up values.
You can graph anything if you can just plug in values.
Right.
Anything you want.
We just can't use a value of 2. But we could use 3 and we could use 1 to get an idea, to make sure that you're in the same correct spots.
So again, our vertical asymptote comes from where we set the bottom equal to 0 and we solve. So our vertical asymptote is at x equals 2. Our horizontal asymptote is at
y equals 3.
Y equals 3 because we shifted up 3.
Yep.
What else do we need? Use limits to
We need the limits. So we need the limits going both ways. So we need the limit from the left and right of the x equals 2 part. We also need the limit as we go to positive and negative infinity. So a lot of limit notation here.
So for h of x, as we're going toward 2 from the negative direction, that means that we're following this line along. We're coming from the negative direction toward 2, and we're going to end up going toward positive infinity.
Yep. And for those of you that limit notation is kind of new, the correct way to do limit notation is how it's being written. Sometimes when you guys work limit notation out, you stretch it all out in one long linear look, and it isn't. It's actually limit over.
Almost like a fraction without a fraction bar.
Right.
Like these go together. We're talking about the limit as x approaches 2 from the positive direction of h of x is, and so if we follow this from the plus direction, it's going to end up going down toward negative infinity. And then our in behavior limits are going to be as x approaches negative infinity of h of x. Well, that's where our
should be
horizontal asymptote is coming in, because as I get closer and closer to negative infinity, I'm getting closer and closer to 3.
And remember, with all these limits, it's what you're approaching, not what you're actually touching. So it's all about the y value that you're getting close to.
Okay, there we go.
There you go.
That's that example right there.
There you go. More vertical and horizontal asymptotes, but oh my, this problem.
Oh, it doesn't look that bad to me.
Well, it's got squareds instead of regular x's.
Okay, so this is going to be a little different. So this is a situation where this may or may not actually look like our parent graph of 1 over x because of the x squareds. I don't know. We'll just have to find out, right?
Yep, let's dive in.
Okay, so...
I'm sensing some long division, actually, for this one.
Really?
My teacher senses are tingly.
Okay, so you want to do some long division?
I don't know. Would that get us into that parent function shape thing?
I suppose it would.
Did you have another plan that was better?
I don't know.
Okay. Don't forget 0x's here, kids.
And I could put a 0x over here.
You could.
Should I do that? I don't really necessarily
No,
have
I wouldn't.
to, though.
No, let's not put it over there. But for
Okay.
sure, we need it under the division symbol there.
Okay, so x squared times what gives us x squared?
1.
So that's going to end up way
Bam.
over here. And so what we do is we multiply x squared plus 1 times 1. We get x squared. 1 times 1 is 1. But we're going to subtract this.
Subtract all of it.
So what that does is x squared minus x squared is 0. 2 minus 1 is 1. And so we end up with f of x being 1 plus 1 over x squared plus 1.
Yep.
So
that's actually a little easier to look at. Gives us a better idea.
Gives us a better idea, I suppose. What's happening here is that this number that we got in front, this 1, that's telling us what our horizontal asymptote is, right?
Because we're shifting up one unit.
Because we're shifting up 1 unit. And so we can say our horizontal asymptote is at y equals 1. And anytime you do this, if you do division, whatever that number out in front is
whatever
going to
the
be,
thing out in front is, actually.
Yes, actually, and we'll look at some other asymptotes that aren't lines that are horizontal. So whatever this is before the remainder is our horizontal asymptote. And then if you don't get anything out in front, then that means the horizontal asymptote's at 0. For our vertical asymptote, we need to look at, on either of these, the way we have them written, where does the bottom equal 0?
So x squared plus 1 equals 0.
Well, we could try to solve that by subtracting 1 over.
That's a great idea.
Square root.
Wait a second.
Oh no. So now that we've talked about real and imaginary numbers, we know that this would be plus or minus I, which is great. Those are some zeros that we have.
Those are the zeros.
But
yeah.
these are not x-intercepts because they're imaginary.
Right, because you can't cross the x-axis at an imaginary spot.
Right. And I didn't mean x-intercepts. I meant asymptotes.
You
It's
meant,
not.
yeah.
It would be an imaginary asymptote,
Right.
which is not an asymptote
Again, it's
at all.
imaginary.
Right. So vertical asymptote would be none. There is not a vertical asymptote.
No vertical asymptotes.
I'm kind of curious about what this would look like.
I know exactly what this would look like, I think.
Okay. You want to tell me about it? You want to
Well,
draw
it's
it?
going to be limiting towards 1 as we go to the infinities. How about that?
Okay.
And if I put 0 in for x,
I get 2.
you get a 2.
If I put in 1,
If you put a 1 in for x,
then that's 3 halves.
yeah. So
is it this kind of
coming,
situation?
yes, it's that kind of situation right there. I'll just double check these, but I'm pretty sure it's a little bump at the origin and flattening out on the limit.
And they didn't ask
No,
us to graph it, but
I
I know we were all
I'm
curious.
pretty certain that what you have is correct.
Okay, well, and another way to check that is that you put in your calculator, or just plugging in more values will work.
Oh yeah, who's right?
Can I see the graph?
No, it looks just like what you drew.
Oh, okay, good.
See?
So our limits that we have to do to describe the behavior is we need to do in behavior asymptotes for our horizontal asymptote. So as x goes to negative infinity
Of f of x.
f of x. As we go towards negative infinity, we're going closer and closer to the y value of 1. And as we get closer and closer to positive infinity, we are getting also closer and closer to 1. And then there's not a vertical asymptote, so we don't need a limit.
Yeah, we
for
don't
the
have to worry
vertical
about that. Yeah. How about that? That's a fun graph.
There you go.
Hey, this is a slide full of, I don't know, rules aren't quite the right thing, but rules.
Yeah,
I
there's some handy tips, tricks, whatever you want to call it.
Tips and tricks to get you through the whole world of
graphing
asymptotes.
A function in general as well, I would say.
Right. So in behavior asymptotes, those are the asymptotes that occur as x goes towards positive or negative infinity, the end behavior. With an end behavior asymptote, we're not necessarily concerned with what's going on close to 0.
No, we're looking at what's happening towards the end.
The end, which is an impossible thing to find, but we can look at a limit as we go towards the end behavior.
And the end behavior asymptotes, most of the time, are also known as the horizontal asymptotes.
But not every time. Some of them are slanted or called end behavior asymptotes.
Right. So
there's some things that you're looking for. Number one, and we'll just go through these really quickly. If the degree of the denominator, that's the upstairs, is less than the degree of the numerator.
You meant that backwards. The degree of the denominator, that's the bottom.
Downstairs, sorry. D for down.
D for down is less than the degree of the numerator.
Right.
There's no horizontal asymptote.
It's what's called an end behavior asymptote or a slant asymptote, depending on what text you're looking at.
And so a degree on the bottom less than the degree on the top, that would be like having x squared on the bottom and x to the fourth on the top.
There you go.
That's going to be a situation where we would end up without a horizontal asymptote. What we would do is we'd have to divide and see whatever that is minus the remainder. There's no remainder for it. And then that would tell us what our asymptote looks like.
The end behavior one.
Yes, the end behavior.
Part 2, then, second bullet point, if the degree of the denominator is equal to the degree of the numerator. In other words, upstairs and downstairs have the same degree, the same exponent, largest exponent situation thing.
So like an x squared on top and an x squared on bottom?
Those would be the same degrees.
What you do is you take a ratio of their coefficients. And so, this could end up being like longer.
There could be tons of stuff.
All we care about is the leading coefficients of the things with the highest degree. So we would make a ratio of 3/1 and have an asymptote of 3.
The reason that we can do that is because if you take, like, say, 1,000,000 and square it, that's a pretty significant number.
Yeah.
But if you take 1,000,000 and then square it and get that huge number and then add another 1,000,000, it's
still a really huge number.
Big, but not quite the same impact.
So
that's
basically
we
can drop off whatever the other terms are and just focus on the ones that are to the highest power.
Right.
Because like if you theoretically plug in infinity and you square it, well, you really don't care about the rest of it because you've already got a really, really big number.
Right. Doesn't make things that different.
Yeah.
Lastly, if the degree in the denominator is larger than the degree in the numerator, then your horizontal asymptote will be 0. Y equals 0.
So denominator larger than numerator. So that'd be like x over x cubed.
That's perfect. And the reason this is true is if you just think about how these numbers grow. If I take the number 2 and put it on the top and take the number 2 and put it on the bottom, well, 2 divided by 8 is a fairly small number. But then what happens when I do it for 100? Well, 100 divided by 100,000?
Something like that.
Is even smaller.
Yeah.
And then 1,000,000 divided by 1,000,000 cubed is even smaller. So
as you make your x values bigger, basically the bottom is going to grow faster than the top because the bottom is being cubed. So that's why it ends up being y equals 0.
So those are easy to see. Those are fun.
Vertical asymptotes. These we've talked about, but they occur where the denominator is 0. And so what you have to do is you always want to factor the top and the bottom. If something cancels out, then that's not an asymptote.
No,
that would be a hole. But I don't think that actually ends up happening in this section.
I don't think it does either, but it is something to be aware of.
But you need to factor anyway because factoring will help you find the vertical asymptotes on the bottom and it will help you find the x-intercepts because that's where the top equals 0.
Right, and if you can't factor, you can always do the quadratic formula on the bottom and get in your rational 0, which is totally possible.
Right. And then the y-intercept, a lot of times we just kind of forget the y-intercept, but if you plug in a 0
for x,
then that tells you the y-intercept.
And it gives us a place that we can actually plot a legit real point close to where we are usually looking, which is on the origin.
Right. And so if we basically this slide is going to be useful if like we're asked to graph something or asked to tell this information because if we know the asymptotes and we know the x-intercepts and the y-intercepts and maybe we plug in a couple other points, then we can pretty easily graph these without ever having to pick up our calculator.
Right, and that's what we want to be able to do.
Yeah.
Okay, so find the asymptotes and the intercepts. of this function and graph it.
Graph it, yeah. So this will play into what we've talked about on the last slide, because almost all of that is super helpful information. Actually, all of that I think is super helpful information.
Especially for this one. So one of the things that we can look at right off the bat is we can look at the degree of the top and the degree of the bottom. That's usually one of the easier things to see. And in this case, we've got a 3 on the top and a 2 on the bottom. So
top's bigger than the bottom. We're going to have to do some division to figure out what our not horizontal asymptote will be.
But our in behavior.
Yes, our in behavior asymptote. So
or slant.
It might be slanted. Actually, this one will be slanted, won't it?
I think this one will be, yes.
Since there's 1 degree different.
Yes, yes.
So we only have an x cubed here, and so this is kind of like a placeholdery thing where, you know, when you have 1,000 and you try to divide, you still have those other zeros.
Yeah.
So make sure that you put those other zeros there. X squared times what is x cubed?
X.
So I put an x here above my other x, and then I multiply. So x squared times x is x cubed. Negative 9 times x is negative 9x, but we want to subtract all
the
of
whole shooting match.
So x cubed minus x cubed is 0. If I drop down this 0x squared, it's 0. And then 0x minus a negative 9x
plus
is
9x.
Positive 9x. And we can drop this 0 down if we want to, but pretty quickly we should realize, hey, I cannot multiply x squared by something and get 9x.
Can't do it. It's pretty much impossible.
So that's a remaindery situation.
It's totally possible, but not for this problem.
Right.
Actually.
So what happens is that anytime we're looking at these in behavior asymptotes, we only care about this first part and we don't care about the remainder. Okay, so you can actually stop whenever you start to see what the remainder is. Our horizontal asymptote, which is really our slant asymptote.
In this case, is going to be y equals x. If there was more stuff in the front, it would be, you know, x plus 3 or x squared plus 2x minus 1 or whatever.
Yeah,
but in this
but
case,
this
it's
line
y equals
x is what we've got going on. So now we've got our slant asymptote. We need to...
Yeah, okay.
We found the slant asymptote as y equals x, and now I think that we should look at the vertical asymptote. And in general, one of the first things we should do when we look at a function is probably try to factor it, right?
Yeah, I agree.
So the top, x cubed, we can't factor.
No, he's done.
But on the bottom, x squared minus 9, I don't know why there's parentheses on the bottom there.
Obviously, I made this slide, and that's what I decided to put in there. So
x squared minus 9, anytime you have two things you can take the square root of.
And there's a subtraction sign.
And there's a subtraction sign. This is the sum and difference of
squares
or something like that.
Yep.
So x minus 3 and x plus 3
Righto.
is what that splits up into.
Bingo, bango, bongo.
Nothing cancels out.
Nope.
But now we can set the bottom equal to 0 and solve to get our vertical asymptotes.
Which it looks like it's going to be 3 and negative 3 because nothing cancels out on top, as Mrs. Stevenson just indicated.
Right. I regret the decision of writing this out. Okay, so x equals negative 3 and positive 3.
Getting closer.
Okay, now intercepts. So how about the x-intercepts?
So the x-intercepts are going to be, gosh,
where the top equals 0.
Has a 0, which would
x
be
cubed
at
equals
0.
0, that'd be at 0. With a multiplicity of 3. Not that it matters. It really doesn't matter that the multiplicity is 3, except that that means that it goes through instead of just bouncing at 0.
Should, yes.
Y-intercept, we have to plug in 0 now. So 0 cubed over 0 squared minus 9. Is 0.
Yep, anything with 0 on the top. Now this is a situation where 0 on the top, good, 0 on the bottom, bad. So
that's always a situation.
Yeah, don't try and create something that doesn't need to be created. 0 on the top is fine, it's just 0. We can totally do that.
Yes.
0 on the bottom is where the issues occur.
Check out my cool graph I've got going on
Wow, that's
here
amazing.
with like tick marks and stuff.
Yeah, that's wicked.
Okay, so we have a vertical asymptote at negative 3, a vertical asymptote at positive 3,
and a slanted asymptote at y equals x.
So that's a line that goes through 0 and has a slope of up 1 over 1.
A lot of crazy things going on here. including that crazy thing.
I don't know if they saw that crazy thing. Okay, now here's something that can be kind of tricky. So we've got these asymptotes going on, and so our graph, that's where our graph is going to be, is it's going to be headed toward these asymptotes, but not touching these asymptotes. So you might say, hang on a second, we have an x-intercept at x equals 0, y-intercept at y equals 0, which means our graph is going through 0, 0, but there's an asymptote right there. Well, what happens is that slant asymptotes and horizontal asymptotes are only in behavior asymptotes. So in the middle, they're not very good at being asymptotes.
No, they're terrible, actually.
Yeah. Because
we're going to cross
horrible.
that sucker, yeah.
Horrible. So would you say at this point they should look at the graph or plug in values to figure out the
I say let's just kind of check out a couple values, because those are, you know, not hard numbers to work with for this particular problem.
So how about like a positive 1?
Okay, so positive 1. So 1 cubed over 1 minus 9.
So
1/8.
Negative 1/8.
Negative 1/8.
Which is important. So we're
right,
going to be
right under the x-axis.
Right here.
Yep.
And then if I plug in negative 1.
Yep, that's going to be negative 1 on the top, and then again on the bottom an 8. So it's positive.
Positive 1/8.
Yep. So I would say, mostly because I'm so familiar, yes, keep going. Because I'm so familiar with the graphs, this is how this interior part should look.
So the interior part is basically going to ignore, wow, I can't talk. It's going to ignore the slant asymptote here in the middle.
Right.
But then on either side, the slant asymptote and the vertical asymptote are both going to come into play.
Right.
So normally, if I'm headed down this direction, that means that up here I would be at positive infinity, because it's
and you're
opposite.
going to squeeze right into that little hole right there.
And then same here.
Thing
this
on the
is
other
up
side.
top, so this will be down low.
Right.
And if you graph this and look at your graph, you'll see that while they did a better job on the calculator, this does look very similar to what we would get.
Pretty similar.
Yep.
All right, so let's find the x-intercepts, y-intercepts, asymptotes, in behavior, all kinds of goodies.
All of this stuff. So
but there
let's
is
start
a
off by factoring.
typo on your notes.
Right. It's important that you change this to a -6 instead of a +6. Otherwise, it
totally
doesn't work out very well.
Yeah.
We're speaking from personal experience.
Yeah, it was really tragic.
Yeah. So we want to factor the bottom here just as a good way of starting out, because if something ends up canceling,
life just gets infinitely easier.
Yeah, so what multiplies to get -6? That will give me a -1 when I add it together.
-3 plus 2.
-3 and plus 2. Now, if we're finding the intercepts, to find the x-intercept, we set the top equal to 0.
Yes. And when you set the top equal to 0, you're going to get a 1. Like 1?
Yes.
Okay.
To get the
Rock
y-intercept, we plug in 0 everywhere that there is an x.
Hey, that's even easier because I know how to do that. That's going to give me -1 over -3 and times -2.
Times positive
-3
2.
times positive 2, yeah.
Which
that's what I
is
said.
-1. You can use either one of these situations to plug it in. But keep in mind that anytime you do that, like the x's are all going to go away because they're 0, and so we should end up with whatever these numbers out at the end are. -1 over -6, which is a positive 6.
That is amazing.
And now the asymptotes. How about some vertical asymptotes?
Vertical asymptotes are going to occur where you get a 0 in the old denominator.
So where does x minus 3 equal 0, and where does x plus 2 equal 0?
-3 and plus 2.
No, at positive 3 and -2.
That's what I said.
That's not what you said.
That's what I said.
Horizontal asymptote.
Hey, guess where the horizontal asymptote is?
If the degree on top is less than the degree on bottom, it should be at y equals 0.
Big fat 0.
One way you can check is if you start trying to divide x squared into x, it doesn't go.
At all.
At all. So
Yeah.
that's y equals 0. What else? Use limits to describe the behavior at the vertical asymptotes.
Ugh. Well, there's 2 vertical asymptotes, which means we're going to have 4 limits.
Yeah. So as x approaches, let's go from left to right. As x approaches -2 from the negative direction, you know, it might be helpful for us to have the graph to do this.
-2 from the left is going to go towards -infinity.
Well, I was going to actually draw the graph.
So I didn't cheat at all.
What do we have? We have vertical asymptotes.
-2 and 3. Little
at
VAs.
+3
Positive
and
3.
-2.
That's right. Never a truer word spoken.
Y equals 0.
This is taking shape here. I like it. I like it.
X-intercept at x equals 1.
Yep.
And y equals 1/6. And so what's going to happen here in the middle is it's going to look kind of like a cubic function in the middle.
And do your best in here. It can be really hard to string all those guys together, but it's going to look something-ish.
And if this is going up towards infinity, then it should be down here for the left side.
Shut the front door.
If it's down here and then it should be up here.
Just like all the other problems that look like this?
Yeah, exactly.
Get out of town.
Yeah, okay. So now, as we go -2 from the negative direction, so as we approach this first vertical asymptote from the negative direction, it's going towards negative infinity.
Did you change your ink? You did. Okay,
I did.
Good job. And as we go towards -2 from the right-hand side now, that means let your eyeballs follow the graph from the positive side.
So this is in the middle. As we go towards -2, we end up going towards positive infinity. And then limit as x approaches.
3 from the left. It's exactly what we did on the previous identical spot.
3 from the left, it's going down.
Negative infinity. And 3 from the right. Totes posies.
Positive infinity.
Oh yeah, that's what I just said.
Okay, and then analyze.
Well, analyzing, remember, is all the
kinds
GUIs.
of stuff, like
so
domain.
Domain. Well, guess what 2 numbers we can't have in our domain?
-2 and 3.
Those vertical asymptotes. Those places in the denominator where we get a 0.
So we can go from negative infinity to -2, and we can go from -2 to 3, and we can go from 3 to infinity, but at -2 and 3, we're not equal to.
Can't
so
have those. And
parentheses.
please make sure that parentheses are everywhere here. We cannot play the guessing game on this. If we guess, you're wrong.
Yeah. If we have to guess between it being a parentheses or a bracket, we're just not going to. We're going to count it wrong. Range. The only issue is that at y equals 0, but wait, here in the middle we do have some values for...
It crosses right through there. Like
so
we've got a
actually
value.
Okay.
Yeah, we're good.
Any y value we want to, we could get an answer for
That's
because
right.
of there in the middle at crossing the horizontal asymptote.
Perfect.
Let's see, what's after
Domain range.
Continuity.
We are not continuous, and the reason we're not continuous is because we have a vertical asymptote. So anytime that you get a vertical asymptote, your graph automatically becomes a discontinuous. Discontinuous
Do you
graph.
not know what the word is?
What are you writing there?
Discontinuity
okay.
at x equals
3 and 2.
2 and 3.
Yes, that's what I said. I feel like your handwriting has suddenly gone
Increasing,
haywire.
decreasing, and constant.
Wow, this is going to be a really involved part because what we want to be able to do is tell where the y values are falling, where they are constant, and where they're increasing. Well, we're decreasing y values from negative infinity all the way up to an x value of -2, and you can tell that because all the y coordinates are getting smaller.
Right. And then, once we get past that asymptote at -2, I just didn't like the way I wrote that. That was right. I just thought it looked a little...
And then if we look again...
From -2 now, oh wait, we're still going down.
We're still going down. So from -2 to 3 now, we are also decreasing y values. Son of a gun, we are also decreasing again from 3 to infinity. That's just crazy.
Yeah, so we're basically decreasing on our domain.
Yeah. Now, it looks like on there's some arrows pointed up, but as you move from left to right across the graph, all the y values are falling down.
Yes, they are. Symmetry, I feel like this could be symmetric across the y-axis.
But it isn't because it doesn't cross through the origin.
Oh, you're right. No, yeah, I'm sorry. No, it's not symmetric.
It looks it though. It does look it.
It looks like, there's some kind of pattern going on.
Right.
But there's not.
If it were to go through the origin, we could quite possibly have a pattern.
Yeah, bounded or not bounded or partially bounded
it's unbounded.
It's unbounded.
There's no floor or ceiling that our graph can't break through. It's that strong.
Okay, Extrema. There's not any maxes or mins.
Correct, because now You might look in these corners for max or min, but the y values are continually changing. They're not approaching a specific height or specific bottom, so there's no extrema.
Yeah, and next we would normally talk about our asymptotes, but I figured we already wrote them over here, so we don't really need to write them again.
No.
So our in behavior limits, as the limit of x approaches negative infinity of f of x. As we go to the left on our graph, we are getting closer and closer to 0. And also as we go
to the right, it's the same thing.
Right. There we go. That's everything. Hi. Find the intercepts, analyze, and draw a graph of the rational function.
Which we have been practicing actually this whole time.
We absolutely have. And you know, until you get used to these, if you need to take a look at what something is in the calculator as you're doing it, that's okay. Just make sure you're making connections between what you're seeing on the calculator and what you're actually doing as far as the math goes here. So,
because you're going to have to be able to reproduce some of these with a fairly accurate sketch on a test without a calculator.
It's quite possible.
Quite indeed.
Okay, so let's start with the intercepts. The x-intercepts you find by setting the top of the function equal to 0. So 2x squared minus 2, I'd add the 2 over to start off and get 2x squared equals positive 2.
Hey, this looks like something we might actually be able to work with here.
Divide by 2, we get 1. Square root both sides.
Plus and minus 1.
That is correct.
Yes.
So we have x-intercepts at x equals positive and negative 1. Don't forget about the negative.
Always important.
Yeah,
negative.
Yeah, definitely. Y-intercepts. Remember we talked about that if we just think about what if these x squareds go away, our y-intercept should be negative 2 over negative 4, which simplifies to be 1/2. But if you are unsure there, just remember you can plug in and find f of 0, and if you do, you get 1/2.
And f of 0 meaning everywhere you see an x, a 0 takes its place.
Yes. Analyze. So
Whoa,
that's
we didn't analyze and draw. We may need to draw first.
okay. Well, let's go ahead and find the vertical and horizontal asymptotes.
Okay, rock on.
So on the bottom here, if I set this equal to 0, I should factor x squared. No, I don't have to.
You don't have to on this one, but you could because it is a difference of squares.
Right. So that would give us x plus 2 and x minus 2.
And if you didn't do that and you just move the 4 over, you'd have x squared equals positive 4.
And either way, we're going to end up with x being positive and negative 2.
That is correct.
So that's where our vertical asymptotes are. And then our horizontal asymptote, if we have one.
Ooh, we do have one because the degree on the top is the exact same as the degree on the bottom.
So it's almost as though like we're canceling the x squareds out. We're not literally doing it, but it's kind of like we're canceling out the x squareds. We're ignoring the negative 2 and the negative 4. So we get 2 over 1, which is 2. So that's y equals 2. Now I think we should have a pretty good idea of what this looks like.
I feel like pretty good at this point in time. Pretty good.
Okay, let me change to a different color. How about pink?
Yeah, now let's put in some asymptotes.
Okay, positive and negative 2?
Yeah. Wow, that asymptote, he walks like a sailor. Oh boy.
Y equals 2 is our horizontal asymptote.
Use your mind and pretend those are all 90-degree angles.
Hey, they're not that bad.
Okay.
The y-intercept is at 1/2, so right here at
there.
1/2.
Yep.
We have x-intercepts at 1 and negative 1.
Yep.
So this is going to look a little different than the ones we've been doing recently, because if you follow this through, like if this is where I'm going through the y-axis, this is going to look kind of like a parabola facing down.
Right, upside downy. And the reason we know that is because we've got to have something going on in there, and nothing goes up. I mean, we've got a high point at 1/2.
Yeah, that's what it looks like. And so now our graph should be at the top left and at the top right, because if I am headed toward this asymptote, headed down towards negative infinity, I should be back up at positive infinity here. Is that what the graph shows?
I believe that is correct. I'm just going to double check
just
these.
double check real quick. Yep, that's
what the
what it
graph
looks
shows.
like.
Yep.
And if we weren't sure, we could plug in like 3, for example.
3 and -3.
Yeah, 3 and -3, and then we'd know for sure where to draw the rest of our graph. So this is 18 minus 2, which is 16 over 5. That's a number that is bigger than
a half.
3.
Bigger than 2.
3.5, 3.2. So this would indeed be up here. And then we could check -3 and we'd find that this is in fact up here. Now that we have that, let's analyze.
Yes, let's analyze.
Let's analyze.
Let's analyze.
How do you feel about this graph?
I feel
is that not the
like
analyzation
this
that we're doing?
graph has reaffirmed my positive emotions.
Okay. Domain. We have 2 problems. We have
I feel like you didn't
-2 and
positively
+2.
reaffirm me with the course of the conversation.
That's not really what we're doing here. I'm not certified to offer you that. I'm only certified to teach math.
It's a good thing.
-2 and +2, those are our 2 issues. So they're what is excluded from our domain. Our range here.
Now pay attention on range because not every value of y gets used.
Because if we're following values from -infinity up to +infinity, we really need to actually limit it from here, which is, we said 1/2, if that really is the maximum.
I feel like it is because according to our graph here, but I'll double check.
Yeah, let's double check.
And so this is an instance also where on your calculator you would just make sure that that maximum at that location is what it says it is.
And so he's going to analyze graph or second calculate if you're on an 84, and then doing lower bound, upper bound.
It says
0.5.
0.5.
So that means that we're going from -infinity to 1/2, and then our graph picks up again
at the 2.
And actually I'm so sorry, but that's a bracket because we said it could equal 1/2. See how I erased that so nicely?
There's no...
It can equal 1/2. It
Yes,
is 1/2
it is 1/2
right there
right
at 0. And then now we would pick back up, and it's not equal to at 2 because we've got an asymptote. It gets really close to 2 but never touches it. Then it keeps going to infinity.
Yep.
That's kind of a weird range.
That is a weird range, but it works.
Okay, continuity.
Continuity means that you can draw your graph completely 100% prettily from left to right without picking up your pencil.
Yes, so in this case, this would not be continuous, and more specifically, we have discontinuities.
Whoa, plural.
Yeah, I went there.
Wow, that's
X
impressive.
equals -2 and +2.
Remember, we said this earlier, anytime you have a vertical asymptote, you're going to have a discontinuity.
Yes, increasing, decreasing, or constant. So
Ooh,
right
this is
here,
a lot of writing on this one, I think.
right here we're increasing,
Yes.
and then right here up to our max we're increasing. Then after our max we start decreasing again. So if we had not yet found out what that maximum was, we would have to do it right now.
We got to say.
So starting with increasing, I'm just going to abbreviate that.
Yeah, ink.
So we're increasing from -infinity until we get to our first asymptote.
Right?
And then from our asymptote until we get to the x value
The x
of
value.
that max.
That's the important part, is we're looking at the x values where these y values increase.
Right, and so we would say that's at 0. And you could put a bracket around 0 if you were so inclined.
You could.
But you don't have to.
In mathematicians, we'll discuss whether or not that 0 is included, but we're comfortable with that,
Yeah,
right?
we're comfortable either way. And then from 0 to +2, and from +2 to infinity. And we leave out the -2 and the +2 because the graph is doing nothing at those points.
Nothing at all, so we can't include them.
Yes. What's after increasing and decreasing and stuff?
Asymptotes, which we've noticed. We've already
How
determined all
about
that. What about in behavior with limits?
Well, that's usually a lot farther down.
Oh.
What about symmetry?
Symmetry. This appears to have some symmetry.
Yeah, I think it's symmetry across the y-axis.
I would say so as well.
And so we can check that really quick by saying, hey, if I plug in a negative x into my function, what happens? And hopefully we pretty quickly, since we've been practicing this, we'll see that, hey, those negatives get squared away, so I end up with exactly what I started with.
Right back to the starting spots.
Which does mean that this is an even function. So this is symmetry across the y-axis.
Symmetry across y-axis is usually pretty easy to see because you could just take your graph and fold it, and
They could be tricky though and make it look close to it.
They could. We had one just a few slides ago that was close but not quite.
Yeah.
So.
Is it bounded? No, it's not.
It is not bounded, although you might want to say it has got a ceiling and a floor. But if you say both of those, then you're not bounded.
Well, okay, we have a ceiling and a floor, but they're in the middle of the graph,
right,
and that doesn't count.
Right.
I decided better spell this correctly.
Yeah, spell it correctly.
We have a max at...
We don't have it. We have a local maximum.
Right, a local maximum at 0, 1/2, and that's it. We have 1, 2, 3, 4, 5, 6, 7. You're all at home probably thinking, oh, well, our asymptotes up here, that was 1. So now we're
we
at
had to talk
behavior.
about asymptotes. Asymptotes.
Asymptotes. In the behavior, using limits.
And it really is important that you write your limits correctly. I know we talked about this earlier, but when you get into calculus next year, your teachers and your AP exam readers have to know what you're talking about, and there's only one way to write a limit.
The limit, as x approaches, whatever your values are, of f of x, in both directions, whether we're going to negative infinity or in positive infinity, we are approaching 2 with our graph, because that's our horizontal asymptote. That should be all of them.
I think we've got the whole analyzation done.
And we graphed it, so we're good.
Fabulous. All right, so what we're going to do now is we're going to show you how to find all these in behavior items on your calculator. And you should see both an Inspire and the 84. On both of these, you're going to have to manipulate your graphing windows to get a graph that is appropriate for what you're wanting to look at. Okay, well, the first window needs to show the area around the vertical asymptotes, like what's going on in those specific things, which is going to be close to the origin for this particular problem.
Should we find the in behavior asymptote real quick?
I mean, we can find an in behavior asymptote because your graph may or may not show that right off the bat. So there's a couple ways to do this. One is long division, but in this case, I think synthetic division is a little bit easier. If we look at that x minus 1 and set it equal to 0, we're going to have that x equals 1 is a 0 for this problem. So when I do my synthetic division, what am I going to have? I'm going to have 1, negative 3, 3, and 1. You
said it was a 0, but you actually meant
what I meant was
that's what solves it.
Right, this is what solves it. Okay. Yeah. So bring your 1 down, multiply, and add. Multiply and add, multiply and add. And we went from a third degree equation to a second degree. So basically what I have is x squared minus 2x plus 1 plus the remainder, which is 2 over x minus 1. Okay.
But for in behavior asymptote, we don't care about that at the end.
We don't care about that guy. We just want this guy right here. So our in behavior asymptote for this particular problem is actually going to be a parabola.
It is. Y equals negative 2x plus 1. So what does it want us to do? Graph it in 2 windows.
So we're going to put it in 2 windows. We're going to show you one with what's going on close to the asymptote.
The vertical asymptote.
The vertical asymptote.
And one showing a graph that resembles the in behavior asymptote. So if you just start off by graphing it with like a normal window, you should hopefully be able to kind of get an idea of what it looks like with the second part, the in behavior asymptote. Hey, what happens if I try to graph the in behavior asymptote with the...
It might cover it up.
You think so?
Yeah.
You think I shouldn't do it?
It's up to you. So you're going to get a graph close to the asymptote that's going to show a graph something like this. And that asymptote, again, this is a rough sketch. You can see a better version right now live with the calculus. But here's basically what your graph might look like.
So if you look at that in behavior asymptote, we really do have like that, the graph is not crossing that. The other thing that's going on is we have x equals 1 is our vertical asymptote because it's where the bottom equals 0. And I don't know how easy it is to draw a vertical line on this, but like if you look, that's the other thing going on here, that we have a vertical asymptote right here at 1. So what do we want to do?
So we just want to show one graph, which is the one you see here.
Yeah.
And then we want to show one graph where we can actually see that in behavior asymptote as an actual feature of the graph without having it specifically in there. So you would change your X and Y range around a little bit.
Okay.
And like make your window, you can either go to window settings and let's go for X, leave the X max alone maybe for the time being and min alone, and change your Y's to be like -50 to +50. What's that look like? So you can see right here a little bit easier that parabola shape. It really sticks out.
Yeah, definitely. Keeping in mind that the other thing going on is that vertical asymptote.
Yeah.
Because if we didn't have a vertical asymptote, it
Highlight,
really would
highlight the blue one again and it'll stick out even more. There you go.
There's our graph.
So that's using your two different windows, and again, you got to be comfortable changing back and forth between windows. But that's how you do it. And you can also see right now the 84 as well. So both of those can be used, you know, to see what a graph shape should look like.
So in this problem, if this was like what they were asking us on the homework, you would definitely need to find the in behavior asymptote, and then when it says for us to graph it, you know, there wouldn't necessarily be a whole lot of work to show there. We just want to make sure that you see what that looks like.
Right.
But you should be able to find the in behavior asymptote by dividing.
Right.
Find the intercepts, analyze, and draw the graph of the rational function. So this is what we've been doing. But whenever we start going here, like we want to find the intercept, so we start with the X-intercept. On top here, if you set this equal to 0, you may have some issues with solving
-0.25.
So don't get ahead of, I didn't even ask for it.
Sorry.
The X-intercept, find it on your calculator. Graph this and find it. So what did you say it was?
I got -0.259.
Okay, so that's our X-intercept. Because we couldn't factor it, we might as well just graph it and use the decimal.
Yep.
But that's a last resort. Keep that in mind. Y-intercept. Everywhere the X is, I put a 0, which is going to leave me over here with
1 over -1.
Yeah, 1 over -1, because everything else is going to cancel out, which means that y equals -1 is our Y-intercept.
That's what it looks like on the graph too.
Analyze. So we've already got our graph up because we had to have it for the X-intercept. Our domain, well, we know there's going to be a vertical asymptote at x equals 1, so our domain is everything except for that, right?
You got it.
How about that range?
How about that range? Well, basically, every value of y gets covered because of the...
Does it really?
Yeah, it actually does because of the left-hand side
Oh yeah,
of the
because the left-hand side, that looks basically like a cubic function.
Yeah, so if you remember to the previous problem when we originally saw this graph, it shot straight up and shot straight down, so
yeah.
we got everything.
So would this be considered continuous?
This would not be a continuous function because you have a vertical asymptote at 1.
Right.
So anytime you've got that vertical asymptote, there goes your continuity,
so
right out the old window.
Discontinuity at x equals 1. And then symmetry?
Symmetry, pretty much no symmetry. Bounded or unbounded, on its domain, off its domain, it's bounded, not at all.
I was like about to say, it is unbounded.
It isn't unbounded. There's no floor or ceiling that the graph does not break through at some point.
Right. Max, min?
It does have a local max, or I'm sorry, it's got a local minimum.
Right there on the right side where it almost looks like a parabola.
On the right-hand side here, so I'll just find that real quick.
So you're going to analyze graph.
Go menu, analyze, and find the minimum because that's the shape that we're looking at.
Or on an 84, do second trace to your calculate menu and then click minimum.
And
we want a left bound, right bound.
Yeah, left bound, right bound. And
that's not really working out for you, is it?
It is. It's starting to work out for me now. So
you can do it.
Here.
No, you didn't do it.
Okay, hold on.
Okay.
Here.
here.
There we go.
And then
hey, look at there.
That's pretty.
2, 3.
2, 3.
Works out great. So
and
we have
that's a minimum because
that's a minimum.
it's a valley.
It's at a valley, and it's a local minimum.
Which local just means at that it dips down at that point. It's
Right.
not the farthest.
No, it's not the
south of
farthest. No,
points.
right. But
it's a minimum.
It's a bounce there.
Okay, so
Increasing and decreasing behavior. So if we look for increasing behavior, since you're writing that first, we're actually going to go to the right-hand side of our minimum. So
Right.
we would go from 2 to infinity. Now, again, we would say you could include the 2 if you wanted.
right. You could if you wanted to.
Or you cannot include it, as it were. They're both going to be acceptable for us.
Now we can go on decreasing from negative infinity until our asymptote, right?
Yes, which is at 1.
And then we can go from 1 until we get to our minimum, which is 2. And that's where it's increasing.
Right.
1, 2, 3, 4, 5, 6, 7. So in behaviors 1, asymptotes. We haven't actually
we haven't
listed
said,
those out.
You're right.
Vertical
So,
asymptote at x equals
1.
1. And we don't actually have a horizontal asymptote. We don't really have a slant asymptote either.
Well,
I
we
guess
do have a slant asymptote. We've got that
But
in behavior asymptote,
Okay,
I
so
guess.
that's
Is,
what I guess we should call it.
an in behavior asymptote.
EBA, in behavior asymptote. It's a thing. Start the trend. So on the previous slide, we did the long division for this. X squared minus 2x plus 1.
I think that was correct, yes.
Yeah, so that's our in behavior asymptote. Our in behavior itself.
With the limits now, and this is going to be what the y value approaches as x goes to infinity.
Right.
So,
And if I like to start with negative infinity.
hey, that's fine with me. It sounds great. It's got a good beat
as we
against to it.
go farther and farther left, what value are we approaching?
Positive infinity, because the graph is going further and further up into whatever.
Then as we're going to the right,
We are going to be going up all the way to whatever.
right, in the middle there we have some other issue, but on the far left and on the far right we are
They're both
going up
going-
to infinity.
Yep.
Let's draw this graph.
Let's look at that bad boy. So we know that it's going to cross the x-axis at negative 0.259, so it's
that's
just barely.
really close to 0.
Just barely.
Y equals negative 1, we've got
Yep.
a point. We've got an asymptote here at 1.
Yep.
And then our other asymptote is y equals x squared minus 2x plus 1. Well, I know that that goes through 1, and so basically it's going to be a parabola that opens up.
Yeah.
Something kind of like
Yeah,
this.
something similar to that.
And so we are kind of using our idea of what we thought this looked like from,
Previous
Yeah.
slide.
well, and from the calculator. So
Right.
I would connect these, and they're going closer and closer to that.
Right.
And then does it do?
I think it's on the other side there. I think it's on the inside.
Really?
I thought. Isn't it going to be on the inside right there?
Oh, I guess so.
I'll double check it. X squared minus 2x plus 1.
And so the thing is, again, this is our in behavior. So, I mean...
So even if it's off just a little bit. Yeah.
It can cross it as long as the in behavior is true.
Oh, it's just outside of that graph.
I just undid the
Yeah,
other.
sorry.
Okay, so it is on the outside. So it kind of follows this curve up
Right.
like this. And then it's inside on these two, right here.
Yep.
Okay, so there we go.
There you go. There's the graph. And just pointing out, we don't know exactly where that parabola is. Now, if we were to graph it, we could find exactly. But the thing is, the rough sketch needs to look pretty good.
Yeah. So I just realized we haven't given them a code word for this section yet.
Code word.
What did you say it was going to be?
Code.
No.
Catatonic caterpillar.
Catatonic caterpillar.
Put that down in a motto. Answer the question. Don't tell your friends.
Okay, and remember, click turn it in and write this in the comment section, or if you turn it in and you forget to write it, you should be able to comment on your assignment or something like that. If all else fails, just direct post whichever one of us you have and
That is
message
correct.
it.
Yep.
But you need that to get some of your points, so please do that.
Yahoo. Have a great day.
Yeah, you too.